Alright, hey AP Chemistry. So, this video is solely going to focus on Quick Check 1 and just some beginning ideas, and I will be jumping a bit around based off of the information that's found on here, but there is a purpose. So, for example, the first question says, sketch the potential energy involved as two hydrogen atoms approach each other. And what that means is, if I have two hydrogen atoms and they're coming close together to bond, to become H2, what does the potential energy look like? Now, I made a note here that this potential energy diagram, that's what it's called, this is found on page 445. That's in chapter 10. So a lot of the questions on here relate to the beginning of chapter 9, but this first 2 or 3 questions ask you to jump to chapter 10, specifically section 10.6. So I'm going to do that, but it's okay, and we'll go back to the beginning of chapter 9. So the way that I would sketch this out is there is going to be a minimum distance that these two hydrogen atoms will hit in which there is bonding. If they're too close, there's a bit of repulsion. If they're too far away, there's no attraction. So the way this potential energy diagram tends to look is there's a minimum that hits and then some other type of minimums. All right? And so this minimum here is going to end up being the minimum distance, and we refer to this as the bond length. And this is actually the lowest energy too, which means the most stable. Okay, and there are other minima, well, there's no other minimums, but there are other lower energies, but the lowest energy is this minimum energy, the lowest point on this curve. And so if you look on page 445, you have this diagram that outlines this exactly the same. Okay, this interaction energy of the two hydrogen atoms. Here's our minimum energy. We call this the bond length, and it corresponds to the bond energy. Anything lower, there are lower points, right? So if I have a lower distance, right, if I get them really close, the energy increases because now there's repulsion. The two atoms are getting too close together that their nuclei are clashing. Versus if I go even further away, the energy becomes a little bit higher as well, because now I have separated the atoms further apart, that there's no attraction. So there's some minimum distance that these two atoms could hit in order to bond. And that's what a lot of chapter 9 and 10 are about, is this bonding. Okay? So we're not going to talk about those energies in this yet, but I do want to have some terms here. As the two atoms get closer, the potential energy drops because of the attraction between the electrons. And what would the electrons be attracted to? Something positive, which what is positive in the atom, which is the nucleus of the other atom. Okay, if they get too close, then the nuclei are clashing, and that's repelled. And then it says the distance when the potential energy is a minimum is called we call it the equilibrium bond length. And that is found on page 446. They talk about that on page 446. So just kind of giving you a little bit of a jump to how these atoms are bonding. In chapter 9, though, you just start drawing and talking about atoms bonding. So we'll talk about that now for the rest of this quick check. Okay? So as you've noticed or read in chapter 9, all of the bonding happens from the valence electrons. Okay? So it says, draw the following Lewis dot diagrams. A Lewis dot diagram is a symbol of the element with dots that represent all of the valence electrons. And if you have a periodic table, and this is just from another handout, on this periodic table, there are certain groups. 1, 2, we skip all of this, 3, 4, 5, 6, 7. And then there is an 8th one for our noble gases, but that's not on this periodic table. The group number corresponds to how many valence electrons there are. So hydrogen is found in group 1, it has 1 valence electron. Boron is found in group 3, sometimes it's called 13, but it's typically group 3, 3A or 3B, that has 3 valence electrons. So that's going to be a big thing in chapters 9 and 10 is how many valence electrons does it have, and that's equal to the group number. So I kind of updated the way that I want you to answer this question. Don't worry about this whole beryllium ground state, beryllium bonding state, blah, 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 blah. I just want, this is an older type of handout where they used to talk about that, but that's not important in the scope of this course. So we just need to worry about how would we draw Lewis dot diagrams for beryllium and silicon. Well, beryllium is in group 2. So if I have a periodic table, beryllium is in group 2, it would have 2 valence electrons. The way that I would draw that would be like this. 1, 2. Okay? And just as an aside note, the way that we do these Lewis dot diagrams is we draw the symbol, and then we kind of put the dots going, it doesn't matter if you do clockwise or counterclockwise, but you do one on each side, and then you pair them. So it'd be like 1, 2, 3, 4, 5, 6, 7, 8. Okay, now it looks like I wrote 15, but I'll put commas. 6, 3, 7, 4, 8. So that's how I would start putting electrons, valence electrons, on Lewis dot diagrams. I'll do the same thing for silicon. Silicon has 4 valence electrons. It's found in group 4. So the way that I would draw silicon would be, I would put its symbol, and then I would do 1, 2, 3, 4. Okay? Now, it's very important to draw Lewis dot diagrams like this. It is a great representation of the electronic configuration because, as you would have known, silicon's electron configuration shows you that it has 4 valence electrons. Silicon goes into the 3s2, 3p2, 3s2, 3p2. All of those electrons are in the valence shell, and those electrons do the bonding. So based off of how many electrons there are, unpaired electrons, there are 4 unpaired electrons. That means silicon typically forms 4 bonds, and it does. Similarly, you see that beryllium has 2 unpaired electrons, so typically it forms 2 bonds, and you'll see that later. All right, now, bonding could either be ionic or covalent. All right, and later on in another video, we'll talk about how you could distinguish between the two using electronegativity. But for right now, simply, ionic, which is in this next example, typically happens between a metal and a non-metal. And that goes like either way back to your first time being in honors or conceptual chemistry where you learned about type of bonding. In the beginning, and I know for a fact it's in chapter 3/4 where it talked about the different types of bonding. Typically, if I have a metal and a non-metal, that's ionic. And so if I want to draw the Lewis dot diagram for calcium chloride, calcium, I know will end up being Ca2+, and chloride will be Cl-1, and I'll typically need 2 chlorides. So the way that I'll draw this is I'll have calcium 2+, and I'll have 1, 2, 3, 4, 5, 6, 7, 8, -1. And then another one, 1, 2, 3, 4, 5, 6, 7, 8. And then a -1 and +2. This is calcium chloride. Now it says, explain how this bond was formed in terms of the electrons. Electrons were transferred from calcium to each chlorine. Calcium transferred 2 electrons, each chlorine picked up 1 electron. All right, now how do I know that? Well, using prior knowledge from chapter 3 or 4 and what you should have reread in chapter 9. Calcium is a metal. Metals tend to form positive ions and lose electrons. Chlorine is a non-metal. It tends to pick up electrons. And so when the 2 of them form, they're not going to have an overlap or a sharing of electrons, it's just calcium's going to give an electron to chlorine. And if you've ever seen a video between calcium, or like a metal and a non-metal bonding, it's quite explosive. There's an explosion or a boom that happens because electrons are being so quickly transferred from the metal to the non-metal. Okay, so if I have to draw a Lewis dot diagram for an ionic compound, I typically write the metal with a positive charge, and then I do the nonmetals with all of the electrons in brackets. The metal, notice the metal has no more valence electrons. Calcium, if I were to draw the Lewis dot diagram for calcium, if I want to do the Lewis dot diagram, LDD, it would look like this, like beryllium, Ca with 2 valence electrons. That's just calcium as a neutral atom. These 2 electrons can do bonding or can react and can be given to another element. That is why it forms a 2+ charge, because it loses 2 electrons to other elements. Okay? Now we're going to draw the Lewis dot diagram for beryllium hydride, or BeH2. Now, BeH2 is going to be a covalent compound. It looks like it'll be ionic, and in a later video, I'll tell you that it's a very polar covalent bond. They are sharing, but very loosely. Like the electrons are mostly on the hydrogens and not so much on the beryllium. So the way that I would draw the Lewis dot diagram for BeH2, they would be BeH, BeH. Sometimes people draw it like this, Be12H, 12H. Okay, and that's because I had a Be, which up here you saw that it has 2 valence electrons, and an H, there are 2 H's that had 1 valence electron, and they kind of bond together. Not kind of, but they do. They bond together. And I don't know if you know, I mean, this is not going to be important for AP chemistry, but I'm drawing kind of like these fish hooks or half arrows. If you take organic chemistry and you get so far, these half arrow means 1 electron is moving and another 1 electron is moving. A double arrow would mean 2 electrons are moving. So anyways, this is what our bond would look like, and later on you might draw it like this with just a line. Okay, so this is BeH2. Now, how is this bond forming? Electrons are shared between Be and H. Okay? So 1 electron and another electron end up in an orbital, an overlap of orbital, kind of going to like the Valence Bond Theory. And you'll see that orbitals can overlap. Orbitals are where the electrons are found. Orbitals can overlap and a bond is formed. And like I said, there are 2 main types of bonds, ionic and covalent. Sometimes we refer to covalent as molecular. All right, and so electrons are shared between the beryllium and H. Okay, now this is a weird exception because in the next question it says state the octet rule. Be and H does not obey the octet rule, and I'm going to explain all of that now. State the octet rule. The octet rule says all atoms tend to want, and this is kind of like a simplified version, all atoms tend to want 8 electrons in their valence shell, aka want 8 valence electrons. And do you know what elements tend to have this beautiful 8 valence electrons? Those are the noble gases. Noble gases tend to not bond because they're good. They're stable, they don't want any electrons, and they don't really want to give up electrons, and it requires a lot of energy for those noble gases to give up electrons or bond. I used to work with xenon in the lab, or even helium, and it takes almost days to get it to form some sort of complex or compound. And that's because I am really trying to hit enough energy for it to bond because it doesn't want to. All right, so it says, is the compound BeH2 obeying the octet rule? No. If you look at BeH2, and I'll draw it like this, beryllium only has 4 electrons, and each hydrogen has 2 electrons. You'll make a note that there are some exceptions to this octet rule. and you will see that in a future video. Okay? So, I'm hoping this quick check was a good introduction and a recap of all of the beginning things I wanted you to get in chapter 9. Make sure you know the difference between how to define, not differentiate, how to define ionic and covalent bonding, and make sure you know where to find valence electrons and the octet rule. In my next video, I'll talk about how we could use the octet rule and valence electrons to draw molecules.